Thank you. Thanks very much, Mike, and thanks for inviting me. And how lovely to see you all. Thanks for coming along. So yeah, I want to tell you about some work that I did, which I hope you'll find interesting. It was in collaboration with Jason Klebers, my PhD student, and with Paul Clegg, who is an experimentalist in Edinburgh, and with Patrick Warren, who's a theorist at the Hartree Centre. So yes, I've got this title that I made up in the hope that it would intrigue you, and well, you're here, so I guess that worked. And my aim for the talk is that by the end of the talk, you'll understand what the title means, and you'll know why my Christmas bells are so colourful. So the talk, the title has various bits to it, so we will need to go through them section by section. Well, the first two words are hopefully fairly self-explanatory given the time of year, but they will be covered in section 1 of the talk. And then the next bit, bijels, I'm going to have to explain to you what a bijel is. And then I've got this bit at the end about universes. So in section 3 of the talk, I'm going to have to explain how the universe works. Well, I mean, we've got nearly an hour, so how hard can it be? Should be fine, right? And I'm claiming that these two things are somehow related, so we're going to compare them once we've looked at them both. Okay, so Merry Christmas, everybody. Merry Christmas. That concludes section 1. Let's talk about bijels. So, yes, indeed. Oil and water don't mix, as I've mentioned in that little advert. In fact, let's check. Here's where are we? Here's a mixture. Not very clear, but I've got it in a jar here. You can probably see it better if I just hold it up. A mixture of oil and water, and I put a bit of ink in the water so that you can see it as well. And sure enough, the oil hasn't dissolved in the water. They are just meeting at this flat interface, and that's the only place they meet. And the reason for that is that oil molecules like this one repel water molecules like this one, in a very similar way to if you have two magnets and you hold the north poles together. They repel. It's actually a force of repulsion. It's not a magnetic force. It's some other forces that have some complexity to them, but the result is the same, that if you want to push these things together, you're going to have to work hard at it. So you're going to have to do some work, put in some energy, and that means that this state of this system, where the two molecules are close together, is a higher energy state than when they're far apart, because you put more energy into it. So wherever you've got an oil molecule in contact or very close to a water molecule, that's a high energy state. So if we have this oil water mixture in the jar with its very small flat interface separating the two, and then I make the interface bigger, so I make it all squiggly like in my cartoon here. So here what I've tried to do is so show you, well, if I swish this about a lot, and then I get something that's not so flat. It's a bit of a mess of swishy interface that's all over the place, and there's a lot of area to it. In fact, it's made a lot of sort of droplet shapes, and that's because I haven't really swished it hard enough to get a very complicated, disrupted interface between them. So if I swish it about and get it to have lots of regions, complicated regions of oil in between complicated regions of water, then there's a big area of interface there. So that state has a lot more oil and water molecules in close contact than when the interface is flat. So this is a higher energy state. And that's why I had to work hard and put some energy into it to get it to do that. So if I do that, and if I can get them really well mingled like that, and then stop and put it down, then this system, the jar full of oil and water, will lose energy gradually to its environment. In fact, it'll lose it by radiating it as heat. I can't feel that it's significantly warmed up. It's imperceptible, but it is actually marginally higher temperature because of the work I put into it, and it will lose that energy as heat, and so it will go to a lower energy state, which means it will go to a state that has a smaller area of surface where oil is in contact with water. So that means it will coarsen, right? That means it has to move the oil and water regions about. It has to squeeze those fluids into different locations in order to get this smaller interface. And so we've got now bigger regions of oil and water and less interface, and it is coarsened. And then it can, lose more energy. More energy will leak out into the environment until it gets back to the state of just a simple interface. Fine. So that's what it'll do. Now, what happens if we take this and we stick a particle in there with the oil and the water? And this is what Jason and Paul did in Edinburgh, experimentally, because there was an experimental part to Jason Kleber's PhD project. And they, in fact, put in nanoparticles. So they're microscopic little solid particles, little beads of silica, actually, just tiny glass beads that were microscopically small. And they put them in with the oil and the water. Fine, so there it is. And this system still has pretty much the same energy as that one does, because it's still got the same amount of surface between oil and water, but it's also got some solid here now in contact with the oil. But if it rearranges itself into this configuration and it puts the particle at the surface, then actually it's cut out a little circle of surface, and there's now less area of this oil-water interface. So less oil in contact with water. This is a lower energy state. Assuming that the bead has no particular preference for being in contact with oil or with water, it likes or dislikes them about the same amount. So, well, the bead has the same surface energy contribution, right? It's got all of its surface covered in one or other of the fluids in both cases, but there's less surface here between the oil and water, so this is a lower energy state. So this state of the system will lose energy, radiate a bit of heat, and go spontaneously to this state of the system. And this is what it does. It puts the particles at the interface. Okay, so what if we have this very mixed up interface, swish it about a lot, much better than I could, do it so that these regions are microscopically small, of interpenetrating oil and water, and put in loads of nanoparticles. That's what they did. So we get immediately the nanoparticles will migrate to the interface, because that's a very quick way of losing energy, lowering the energy of the system. And then we've still got some bare interface between oil and water, so that will shrink as it loses more energy, and the system will coarsen, just like it did before, by moving fluids around, until it gets to a state like this, where actually there's no more space on the interface for the particles. They're completely crowded together now. And if, in order to make this interface any smaller, what the system would have to do is pop one of the particles out from the interface into one of the fluids. But in order to pop a particle out, it's going to have to leave a little bare patch of oil and water. So actually, that will be a higher energy state for a moment until it manages to jiggle the particles around and contract the interface a bit and fill the gap with the other particles. So in order to pop a particle out, it will actually have to go up in energy, somehow spontaneously get some energy from somewhere in order to do that before it can then shrink the interface anymore. And it can't do that. It doesn't have a spontaneous source of work in order to get that energy contribution. So it doesn't. It's stuck, and this interface won't shrink anymore. So this is this mixture. It's like an emulsion, where you have in emulsions you have droplets of oil in water, and they're stabilized differently. They're stabilized by some emulsifiers, which are molecules that have parts that are attracted to oil and parts that are attracted to water. This is a different thing. It's a kind of emulsion because it's got oil mingled with water, but it's being stabilized by the interface being jammed. There's this traffic jam of particles there. And so it's in this state where it's not droplets of the one fluid in the other. Each of the fluids is continuous and forms this three-dimensional labyrinth, intermingling with the other labyrinth. So it's bicontinuous. So what we have here is a bicontinuous, interfacially jammed emulsion gel. And they're called bijels for that reason. I mean, it's a bit of a cheat, isn't it, using the L from gel in this acronym, but that's what they're called. So these are a new type of material. They were proposed theoretically, actually, first, and that was in 2005. And then a year or two later, the first ones were produced in response to that theoretical paper, produced experimentally. And there's been a lot of development, and there's still a lot of research going on into bijels because it turns out they have a lot of useful applications. Some of them are they're being developed as the next generation of batteries, which have very high efficiency. So to make an efficient battery, you need the electrode to be very, very close to the chemicals that are giving up the charge. Because otherwise, if you've got a big mass of chemical and an electrode far away, then the little charges in the chemicals need to slowly diffuse a long way to get to the electrode. So if you make one of these regions actually conducting, then it will be the electrode, and you put the chemicals of the battery as the other region, and you've got them in very close contact, and you can very rapidly charge them or discharge them, get energy in and out, so they'll be very efficient batteries. Because you don't have to use simple oil and simple water, you can substitute those with similar fluids that don't mix, and you'll still have a bijel. Also, they are used already as catalytic microreactors. So in chemistry, if you want to react two chemicals together, it's hard to do if the chemicals don't mix, because then they only meet each other at a very small interface. But here, if you have this arrangement of materials and you want to react these two chemicals, then actually there's a lot of interface because the beads are round, and so they don't perfectly cover the interface. Wherever you have three of these beads, there's a little sort of curved triangle in between them of just bare interface between the two fluids, and there the reaction will go on through all these little pores in between the particles. So you've got actually a massive surface area in contact, and it can be used to encourage chemical reactions to happen very quickly between these, or in fact biological reactions as well. People are developing methods for using biological fluids and having enzymes in the immiscible fluid that are then going to be in very close contact and work on the other fluid. And also people are developing bijels that are made from materials that are compatible with human tissues for use as surgical implants. And there are other developments being made. And I don't know much about any of them. This is not what I've been doing. Applications. I'm interested in how bijels work and in modelling them. And so Jason did this PhD project in which he started by experimentally making some bijels. And these are some of his photos. This is under a microscope. The scale bar here is 200 microns. That's a fifth of a millimetre, right? So each photo is a little over a millimetre wide. And And I think the orange bits are the oil, and under the lighting conditions that they use, the water is shown dark. And also they use lighting conditions where the particles glow green. So you can see, can't you, that the particles have gone to the interfaces. Sure enough, we do have bijels in each of these cases. So he was able to make them, study them, look at their shapes. And what we wanted to do in our project was to better understand these bijels, and in particular, we wanted to understand how the particles arrange themselves, in what ways they arrange themselves on the surface, and how those arrangements of particles influence the shape of the surface, and how the shape of the surface influences the arrangements of the particles. So, we need to think about that. If you have a lot of little beads, how do they choose to arrange themselves on a surface? So I'm grateful to my son who kindly found his old marbles collection for me, so that we can see what little spheres do when you put them on a surface. And I've got a surface which is a plant pot tray here, so it's flat, and importantly it doesn't have any straight edges. And there are no straight edges here either, just spheres. So let's see how these particles arrange themselves on this surface. I expect you've done this experiment when you were at school at some point, quite likely. Okay, so everything microscopic is always jiggling about a bit, doing Brownian motion, so there's always some little bit of jiggle. So they jiggle themselves around, and if I make them dense enough, then just spontaneously they form these straight lines. Let's do it again. So yeah, I've got straight lines forming amongst these arrangements. Now this isn't a perfect hexagonal lattice, right? It's got lots of bits that are a bit shonky here, right? There's gaps, there's particles in the wrong position for it to be a perfect hexagonal lattice. But it's being a bit like a hexagonal lattice, and it's spontaneously choosing to form straight lines. So it's got that kind of ordering, it's ordered itself in that kind of way. And that type of ordering that is almost perfect hexagonal ordering, but isn't quite that, but still has rather long straight lines in it, is called hexatic ordering. So we want to understand how hexatic ordering works, and that's something that has been studied in the past. Okay, so here's how to represent the important features of hexatic order. Let's think about just a few of these particles. So there's loads of other particles all around them, but I just want to look at 7 of them. So here's a particle and its 6 nearest neighbours, which are not quite in a perfect hexagonal arrangement around it. The important features are these. That's almost a hexagonal arrangement, and so what I can do is draw straight lines between the centres of all the nearest neighbours and measure these angles. I don't care about the distances. That doesn't matter. The distances are wrong for a perfect hexagonal lattice. It is making lots of little gaps in funny places. But the angles we saw were following straight lines. So look at the angles and measure what those angles are. And if they are all exactly 60 degrees, then we have the highest degree of ordering that we can have. So we would say that's a large magnitude of hexatic order at this place. Whereas if we've got a variety of different angles that are very different from each other, then that's low hexatic ordering. So we look at how distributed these angles are, and there's a well-defined mathematical way of defining exactly what we mean by this amount of hexatic order in terms of how different the angles are. Okay, so let's think about that in a large collection of particles that are in this hexatic state. And I just grabbed this image off the internet. It was a good one. It's made by a computer scientist called Lester Hedges in Bristol. And what he's done is color-coded each of the particles. He's simulated a hexatic state and then color-coded each particle by the degree of hexatic ordering, how large this hexatic order parameter is. So yellow is the highest degree of ordering and dark green is the lowest degree. And you can see that there's some largish regions where it's quite ordered, and in between there's some misordered, sort of randomized bits. So the color gives the quality of the ordering, but there's also a direction to the ordering. So I can draw some arrows to show the direction of those nearest neighbor bonds, if you like. So there's an arrow over here along the line of centers. I mean, I could have done it in a 60-degree different direction. It wouldn't have made any difference to the argument. So one over here, and there's one over here, and these are pretty much perfectly parallel. Even though there's some wrongly ordered bits in between, the direction of these nearest neighbor bonds persists over really long distances much larger than the size of a particle. Okay, so this then is what particles choose to do, what spheres spontaneously choose to do on a two-dimensional surface. They form this hexatically ordered state that has a magnitude given by the color, the amount of the ordering, and it has a direction. And it chooses to keep that direction parallel over large distances. So somehow that's its favorite state. So if I was to force it into a state that was different, change the arrangement so that I had rows over here that weren't parallel to nearby rows, then I would have to disrupt the system. I'd have to do some work in order to do that. So that presumably would be a higher energy state. So this is actually its favorite state. So it's in some sense a low energy state of the system. It likes its hexatic order to be parallel over long distances. That's what hexatic order does. So we've understood now that the physics of that. That's what it does on a flat surface. But what we have in bijels is these hexatically ordered collections of particles on curved surfaces, right, between the oil and the water. So how do we describe that? What does hexatic order choose to do on a curved surface? Well, to understand that, let's think about a slightly different system from a bijel. Let's think about a Pickering emulsion. A Pickering emulsion is just the same as a bijel, but for the case where you don't have continuous regions for both of them. It's not bicontinuous. You have discrete droplets of oil in the water, but they're stabilized by particles in the same way. That's then called a Pickering emulsion. So that's slightly easier to think about because spheres are a simple shape. Okay, so we need to think then about how the hexatic ordering works if it's on a spherical surface. Right, so we've established that particles choose this hexatically ordered state and they like to have the direction of the order parallel everywhere. This is rather like the fur of a dog. If you're brushing a dog, you like to have its fur lying parallel everywhere, and then it's a well-groomed dog. And so to understand what's going to happen on these spheres, we have to address the fundamental question of physics of how to brush a spherical dog. It's troubled the greatest of minds for many years. So imagine, if you will, a spherical dog. What am I saying? This is the age of Instagram. We don't have to imagine it. So it's real. There's a dog groomer in Japan who does this to dogs. So I'm assuming that the dog underneath that fur isn't actually spherical, but let's assume that it is, okay? And we want to brush this fur to be orderly and parallel everywhere. Then there's a problem with a spherical dog. You could brush the fur round and round its tummy and its back like that, but then you'd have a whirl on the top of its head and at the other end. So in those places, it's really not parallel at all. Or you could do it so you brush it along the sides of the dog and along the back, and then again it'll come away from the crown of the head, and there it really won't be parallel, and then the other end you'll have a tuft and you'll have to find somewhere to stick it. So this is the same issue that you get if you try to draw a grid on a globe, right? If you're trying to make a map, then you can draw grid lines like these lines of longitude, and you can make them parallel to each other, but they're not going to be parallel everywhere. They'll come together at the poles. So this hexatic ordering of the particles, it's going to be unhappy. It can't make itself parallel everywhere on a sphere. And similarly, on our bijels, which are not spherical, but still they're curved, and that is going to create the same kind of problem to a lesser degree. All right, so that's what we tried to model. So here's one of Jason's photos of one of his bijels, and we want to simplify it so that we can represent it mathematically, because it's too hard otherwise. And so we noticed that it's basically made of pipes, wobbly pipes of oil, or you could think of it as wobbly pipes of water going through the gaps between the pipes of oil. And so they are basically a bit like cylinders, but they're bulgy. We can see some regions where it's very much like a bulgy cylinder. And so we've idealized this by saying, okay, let's write down a mathematical function, a mathematical equation for a surface like this, which is a cylinder that undulates like that. And it bulges by some amount A, and we can vary that in our analysis. So we can study either perfect cylinders or different degrees of bulginess. And we want to describe a system that is a surface like that with some hexatic order that is described in the standard ways that have been studied for many years about how this hexatic order, what its energy is when it's parallel or not parallel. But it's been described on flat surfaces, and we need to put that description on a curved surface. So how do we do that mathematically in order to find out what this hexatic direction does? Does it do something like this and make these sort of whirls around different places? Does it end up ordered? We need to find that out. We need to write down a mathematical description of that. So how do we do that? It's a bit hard to see how that will couple to the curvature of the surface. And so we took inspiration from another area of physics, the standard model of particle physics and cosmology, which actually treats mathematically the same kind of problem. Now, I can't take credit for noticing the connection. That was noticed by others in these 80s and 90s, Nelson and Israelashvili. But yes, so let's study this other system, the universe, which has a well-developed mathematical description of it. How does the universe work? Yep, I'm going to have a go at this. Okay, so the universe, you may have noticed, contains some stuff. Some of that stuff is force fields, like these electric and magnetic fields. And you'll recognize this as an electromagnetic wave immediately if you're one of the physicists in the audience. And if you're not, you might remember it from science lessons at school as the classical picture of a light wave or a radio wave. What's going on here is in the green bits of the picture are representing an electric field. So that's something that applies forces and it points in a certain direction. And we can see that in some it's always pointing upwards and downwards, and in some places it has a large magnitude, and in some places it has a small magnitude, and in some places it points in the other direction. And then we've also got, along with that, a magnetic field, which is represented by the purpley blue bits. And that's at 90 degrees, it turns out, to the electric field. And so that has a certain direction, and it has different magnitudes in different places. And it's well understood how the changing one of these fields makes the other, interacts with the other one and makes it change a bit. And so together they keep changing and keep altering the other field, and it creates a ripple that just propagates then through space. And that's what a radio wave or a light wave is. And this is understood how the physics of that works. And it's described mathematically in terms of these quantities that have a direction and a magnitude about them. Okay, so that's fields which make waves. And then there's other stuff in the universe which is matter, like an electron. Here's a couple of electrons. They're not really hard beads, they're point-like objects, but they have an angular momentum that they carry, so they spin. And the axis of that spin that these particles have defines a direction. So to describe the physics of electrons, we need to talk about the direction that they have. So they have a direction about them. It turns out they also actually have a magnitude about them, just like these force fields do, because really electrons aren't just points in one space, in one position. You might have heard about some of the weirdness that the universe has at the quantum mechanical level for microscopic objects like electrons, that the quantum mechanical physical universe actually doesn't allow them to have a definite position, but they are somehow smeared out into a distribution of probability, and they have different probabilities of being in different places. So we actually describe them in terms of something that has a direction and also a magnitude of this wave function, which is a probability field. So actually, matter is also a type of field, and mathematically we write it down as a type of field. It's something with a magnitude and direction. So we have force fields and matter fields. And if we know the arrangements of them, how large they are and in what direction they point at different places in space, then we understand the physical laws and how to write them mathematically to work out the energy of a state like that. And also its dynamics. If we know the energy, then we can work out its dynamics, how it will change from moment to moment and become different shapes and different arrangements of forces and matter. So that's all well understood, and we know how to write down the maths of that kind of thing. Fine, so that's forces and matter. And there's one more aspect to the universe that we have to think about, which is gravity. Now, gravity isn't like other forces. Einstein discovered that actually gravity is about the shape of the universe itself. And if you're not a physicist, you still might have heard people talk, in popular science programs on telly about Einstein's theory that gravity is curved space-time. Which is a bizarre phrase to use, isn't it? It is confusing. How on earth can the space and the time we live in be curved? What on earth does that mean? And why on earth would that give rise to us feeling a force? How on earth can that work? So, well, I want to actually give you some insight into that and show you how that does work. So let's not try to think about a curved four-dimensional space-time. That's too hard for anyone. So let's simplify the issue and pretend that the universe is two-dimensional, because it's easier to think about two-dimensional things. So let's pretend that we live in a two-dimensional universe. And in fact, this idea is not new, thinking about a two-dimensional universe so that we can think more easily about dimensions. This is an idea that is very old. It goes right back to a book called Flatland, here's a first edition of Flatland. The subtitle is A Romance of Many Directions, a Romance of Many Dimensions, and by authorship is attributed to A. Square. It was actually written by Edwin Abbott, who is a mathematician, and it was written in 1884, long before Einstein discovered general relativity. But mathematicians were already thinking about how to understand hypothetical spaces with different numbers of dimensions, and Edwin Abbott chose to just write a novel to make it accessible to the general public, to help people think about different numbers of dimensions. And so he invented this concept of flatland. And what I'm going to show you is not in that book, but I'm borrowing the idea from his book, as many physicists do. So here's my little sketch of some flatlanders. So these are beings that only move in 2 dimensions. So they can go left, right, and they can go up and down, but they have no concept of depth. They don't know about that direction and that direction. There is no such direction, right, in their universe. It's only 2-dimensional. Right, so there they are, and we, from our higher dimensional vantage points, can see them side on, but they only see each other as edges, lines. So actually, I should have shown you their internal organs and their brains as well, but I thought I'd respect their privacy. Now, these 2 flatlanders are doing an experiment. They've got some cannonballs here, and they're going to launch them from these catapults. I guess they're catapult balls then. And so here they go, ping, and they launch them outwards into space. Or strictly speaking, it's not space, is it? Into area, into the void of deep area. And so they move along straight lines. And this flat universe has a flat Isaac Newton in it. And as you'll know, flat Newton's first law of motion is that a body continues in a state of rest or uniform motion in a straight line unless acted upon by an external force. So they watch these cannonballs and they notice that although they start off in straight lines moving parallel, their paths come together and they collide. And so the flatlanders conclude that there's a force between these particles and it must have pulled them together. And it's the force of gravity. It's a force that these masses have and acted on each other. Now, these flatlanders believe that they live in a flat universe like this, where they could, in principle, tile it with squares. And they could put squares all over their universe forever, and they would all fit together perfectly. Because that's how they experience things locally. But actually we, from our higher dimensional point of view, can see that they're wrong. They actually live on this surface of a sphere. Now, on the sphere, you can't put squares together and keep going. And in their experiment, they launched their particles along parallel paths that were initially parallel to the equator, and they didn't deviate from those paths, actually, due to a force making them curve, but parallel lines meet if you're not living in a flat universe. The same thing is true in our universe. It really feels like we live in a simple geometry where, from common experience, we can create cubes, cubic boxes, and we can stack them, and you can keep going. And so our common sense tells us you can keep going forever. This is not true in this universe. If you keep on going over astronomical distances, those angles won't meet up anymore. They don't work. Just that's how space is fitted together. That those columns of cubes will start overlapping, and it just won't work because we don't live in a space that is joined up in that way, just like they don't. Okay, so that's how gravity works. That's not the whole explanation, because I've shown you these particles, these cannonballs, moving in a space that just has a fixed shape, a fixed geometry. In the real world, masses don't only follow those straight paths through the curved space-time, and we're not going to go into that, but they also change the shape of it. Just their existence actually warps the space and changes the amount of curvature. But still, this is why they follow paths that come together. So that's how curved space creates a force. Right, so we live in a universe like that. And here's a two-dimensional version of it where it's wobbly, and so you can't draw perfect squares on it. And in fact, its shape is changing due to masses moving around in it. Or even without masses, it has some dynamics, and this shape of it will wobble and ripple along, and that's what a gravitational wave is. And these were observed experimentally just a few years ago. So that's the type of universe we live in. That's the shape of it. Let's put it all together. We looked at the things that were in the universe and the shape of the universe. So putting it all together, here is the most ambitious title I've ever written on a PowerPoint slide. But let's go for it. So here's everything. We've got these fields. We understand how to describe them in terms of their magnitudes and directions, and how the energy and the dynamics works if we know what those magnitudes and directions are. If they live in a simple space, but actually they are in a space that is curved and wobbling, and we need to write down the maths of how to describe this kind of problem in a curved space. Right, so that's the universe. We've done Bijels and we've done the universe. And I think maybe you've already seen the similarities. So in each case, we've got something with a direction and a magnitude. Here it's the hexatic field, the hexatic order field. In the universe, it's other fields. And we want to put it into a curved geometry where you can't have things staying parallel always. And we want to write down how to do the maths of that so that we could solve it and see what these bijels will do. Fine, so because of the similar geometry, the similar symmetries, we can take the maths from the standard model and cosmology in order to describe our bijels. So they have similar maths. Now, there is an unspoken rule that in public lectures on physics, you don't show maths. What's that you say? It just doesn't feel like Christmas without some serious integral calculus. Oh, all right then. This is what it looks like. Yeah, so there's the energy, and this is how we describe it for the bijels, and there's some contributions to the energy from the shape of the surface, and there's some contributions from the hexatic order field, and they all add up with some covariant derivatives. And then you have to think about how this works in the specific shape of those undulating cylinders. And then you need to think about how to do it for all possible arrangements of the hexatic field on those cylinders, at which point the maths gets a little bit tricky. But I want to show it to you because I want to tell you about a really simple, useful mathematical method that you can use to get from line 1 through to the final solution. All you have to do is get a PhD student. So I cleverly did that, and after a couple of years of supervision meetings and us talking about this thing, he came to me with some rather lovely results that are colour-coded in terms of pictures. Big sigh of relief. Right, so back to pictures. So here is his colour coding. This is just the key. So this shows us the direction of the hexatic order, so relative to the centre of the picture. So hexatic order that's pointing that way is coded green, and that way it's coded blue. And then there's also brightness and darkness that goes with distance from the centre, and that is coding the amount, the quality, the degree of hexatic order. Okay, so there's the key, and he studied this for different amounts of undulation of our cylinders, and there is a cylinder that is undulating just a bit. It's almost a true cylinder. And here's the result. This is the state of the hexatic field that minimizes the energy. And look, it's all green. It's all pretty much the same shade of green. So it's all pointing in the same direction relative to the grid lines on that cylinder. It's staying as parallel as it can on that surface. Right, but what about when we have more bulgy undulating surfaces, or in fact, for all varying the amount of undulation? Let's have a look at his results. So he came to one meeting with this picture, and my first reaction was, that would make a fantastic T-shirt. Don't you think? Let's have a look at it in detail. So the pictures at the top here are the cylinders unwrapped, right? So that direction along the cylinder is that direction, and the round and round direction is up and down. And the pictures on the left are for no deformation, so that's a perfect cylinder, and everything is perfectly parallel on that cylinder. And over on the right, we have very deformed cylinders that are almost touching themselves at the narrowest point. And we see that as we increase the deformation, it remains more or less parallel as it can be, but the degree of hexatic order isn't the same everywhere anymore once you deform it more. We've got these dark bits. As you're on the bit of the cylinder that's coming towards the neck, then it's harder for it to stay parallel. There isn't really a parallel, and so it actually reduces the amount of order there in order to allow itself to be more parallel in the other bits. And that's the energy minimizing state. But then you cross a threshold of deformation, and it totally changes. And now what it does is it actually creates some of these worlds, vortices in the hexatic order field, where there is zero order, so it's dark. And around them, the direction twists through a full turn, so it's going through all the colours around it. And on the narrow neck, it's hardly ordered at all. It's very randomized particles. So these are the results that we find. And they're rather lovely and interesting. I hope you'll agree. So let's conclude. First of all, now you know what my Christmas bells are, right? I cut and pasted them from Jason's thesis and added some holly. In conclusion, what did we find? Well, the most important result, as far as I was concerned, was that Jason passed his PhD viva about a month and a half ago, actually, which is a huge relief, because when someone comes and gives up 4 years of their life to do your research project, you feel some sense of responsibility that you hope it goes well. So yes, it did. Of course, he'd done brilliantly. What else can we conclude? Well, I hope you'll agree that soft matter physics is pretty interesting and interestingly pretty. In fact, at his PhD viva, I did the standard traditional thing that a supervisor does. I gave him a bottle of champagne, but I also gave him something else that I'd had made. See, was I right? It makes a great T-shirt, and a unique one. Well, almost unique. I couldn't resist getting 2 printed. So, on with our conclusions. I mean, come on, good T-shirt, right? Okay, it's not the only purpose of the PhD, but I was pleased with it. So, he found, as a result of all this hard work, that this orientational order on the surface, it can stabilise the bijel, or it can destabilise it, actually depending on the details of the interactions between these particles, whether they're perfectly hard, whether they are a little attractive, whether they are not quite round. So it's a subtle thing and worth all the effort. He also discovered that if the particles are rather large, then actually, disappointingly, the order doesn't have any influence over the shape of the surface, but the shape of the surface does have an influence over the order. So for big particles, it turns out that all that matters is how deeply they're choosing to sit in that interface between the oil and the water, whether it's around the equator or whether they're a little bit, proud, sticking out into the oil or the water. If they are, then the way they pack actually imparts a bit of curvature to the interface immediately, and that has a dominant effect on whether the bijel is stable or not. And we can also conclude, I hope, from this, you've seen that fundamental physics gives some insights into soft matter physics, and we used those insights to construct the model that we worked on. And I hope you agree that my talk on soft matter physics has given you some insights into fundamental physics as well. Thanks for your attention.